In this section, we are going to talk about how to change variables in multiple integrals. Now, we've already seen this in a few cases. We've changed to polar coordinates in double integrals. And we've seen how to change to cylindrical coordinates or to spherical coordinates in triple integrals. But in this section, we're going to learn how to do that more generally for any kind of change of variables. All right. Now, before we jump right into the multivariable case, as usual, it's a good idea to recall the single variable case. It's going to give us a lot of intuition on why we need to do what we need to do in the multivariable case. So let's consider a single variable integral. This is a simple calculus one-level integral. Let's take the definite integral from 0 to pi over 2 sine of 2x integrated with respect to x. Okay, so how would we evaluate this integral? Well, the usual way to do it is to do a substitution. So let's let u equal to 2x. And if I take the derivative of u with respect to x, I get 2, right? So du over 2 equals dx. And so by making the change of variable from x to u, I'm now integrating, instead of sine of 2x, I'm integrating sine of u, and I have to swap out dx for du over 2, which I will write as 1/2 du. Okay? And of course, my limits of integration change from 0 to pi. They were at x equals 0 to x equals pi over 2. Now they're from u equals 0 to u equals pi. Now, where did this factor of 1/2 come from? Why is it there? So it helps to understand this geometrically, and that's what I want to do with this. Okay, so let's graph our original function, and then let's graph our new function and compare and see why we need that extra factor of 1/2 in there. Okay? Okay, so I'm going to graph sine of 2x. So let's just space things out here a bit. Okay, and I'll just focus on the interval from 0 to pi over 2. Okay, although I'll graph it all the way to pi. But we're integrating from 0 to pi over 2, right? So sine of 2x, notice what the 2 is doing, by the way. It's transforming the function. We take our usual sine function, sine of x, and we're compressing it by a factor of 2. It's going to be half as big horizontally as it was before. Okay. Let me add a couple labels to our vertical axis here. Okay. So if I plug in pi over 4, 2 times pi over 4 is pi over 2, I get 1. If I plug in pi over 2, I get 0. 3 pi over 4, I get -1 pi, and back to 0. Okay. And just connect the dots with the usual sine curve. Okay. And I'm integrating from 0 to pi over 2, so I'm calculating the area under the curve from here to here. Okay, that's the area this integral is calculating. Now, let's compare that to this function. And I really want to emphasize this. In a way, we're changing spaces. Our integral started as an integral over variable x. But by changing the variable, we change the space. So now our horizontal axis is variable u. Okay? So now sine of 0 is 0. Sine of pi over 4 is root 2 over 2. That'd be about there maybe. Okay, sine of pi over 2 is 1. 3 pi over 4 is again root 2 over 2. And then pi. Okay, and I want the integral from 0 to pi. Okay, so what just happened? By changing the variable from 2x to u, I took my original area that I was integrating over, this area right here, and I stretched it out. I effectively stretched it out. So now I'm integrating all of this area. Okay, I stretch it out so it's 2 times as long as it was before. Which means, what's happened to the area? The area that is in here that I actually want to know, if I stretch it out this way by changing variables, it's now twice as much area as I had before. Okay, which is why I need that factor of 1/2. That factor of 1/2 corrects for the transformation, for any stretching or compressing that happens. Okay? We're going to need to do something similar in the multivariable case. We're going to need to correct for any stretching or compressing that happens when we change variables. So let's think about the multivariable case now. Okay? Now imagine I have some double integral over some region E of, in my original coordinates, f of x, y. Okay? So imagine maybe this is region E. Maybe. Okay, just as an example. Hypothetical. All right? The idea here is maybe for whatever reason, this is hard to integrate over. Maybe the function is difficult to work with. And so I want to make a change of variables. So I want to switch from x and y to 2 new variables, maybe u and v. Okay, that's going to change our old space E into some new space. I'll call it E prime. Okay. Maybe prime is not the best notation. In calculus, we tend to associate primes with derivatives. Maybe I'll call it E star. Okay. I just want to emphasize that it's like E, but it's taken from E, but it's not quite E. Okay, so this was in XY space right here. That was our original E. And what we're doing is by converting to U and V variables, we're changing into a new space, UV space. And maybe this E is transformed into some new shape, new region, E star. Okay? Now the question is, in the transformation process, how did this region change? Because we're stretching it, we're shifting it, we could do all kinds of things to it. In that process, are we making the region bigger? And if so, we need to correct for it. Or maybe in the process, we're squeezing region E down, and so it now covers less area. If so, we need to correct for it by multiplying by some kind of integration factor here to correct for the transformation. Okay, just like up here, when we made the transformation here, the area we now had was twice as big as it was before. So we had to multiply by an integrating factor of 1/2 to correct for the transformation that happened by making the substitution. Okay? So how do we find the appropriate factor here? So the factor here, and let me give myself a little more room here, it's called the Jacobian determinant. There are a few different ways to notate it, but I'm going to notate it as partial x comma y over partial u comma v. And then we want the absolute value of the result that we will get there. Okay, so what is this Jacobian determinant? Well, the Jacobian determinant is a way to measure the change when we go from one space to another. Okay? And we can calculate it by taking the determinant of a matrix. So here we have a 2x2 system, right? We started with 2 variables, we're going to 2 different variables. So we're going to have a 2x2 matrix. The matrix is going to consist of partial derivatives. So partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. And then we take the determinant of that matrix. All right? Now, going into the details of why this works is a little bit beyond us in this class, but we could kind of see why this might be the case. For example, if we take a look at this, we're looking at how much x changes per change of u, per unit change of u. So if x changes a lot when per unit change of u, then what are we going to have to do? Okay, it means this had a big area, but this one has a small one. So we're going to have to multiply by a bigger number. Okay, if x changes just a little bit per unit change of u, then that means the original area that x covered is very small. But u is covering a large area. So to correct for that, we'll have to multiply. Our integrating factor here will have to be a smaller number, something maybe smaller than 1. Okay? Now we're just looking in one direction. You really have to consider all directions and all variables to see what to offset your new function by to correct for the transformation of changing variables. Okay. Now this is the Jacobian determinant when we're integrating over 2 variables and we're changing to 2 other variables. It's a similar situation when we have 3 variables. Maybe we're starting with x, y, z, and we're changing to 3 new variables, u, v, w. Okay, we want the determinant of the partial derivatives of our old variables with respect to our new variables, which means we need to find a relationship between our old variables and our new variables. So when we make a change of variables for a triple integral, we will need a 3x3 determinant. Our Jacobian determinant is a 3x3 determinant. Notice our old variables are always on top. Our new variables are always on the bottom. So we want to express our old variables in terms of our new variables and take the partial derivatives. Okay. Once you have the Jacobian determinant, either you're for a 2-variable system or a 3-variable integral, you want to make sure you take that Jacobian determinant and take the absolute value of it. The reason for that is the Jacobian determinant doesn't just measure the change in area or the change in volume going from one space to another space. It can also measure if anything changes direction. So for example, maybe, let me change colors here actually. Maybe this vector in this space maps to this vector in this space, okay? And this vector in xy space maps to this vector in uv space. What that means is they've kind of swapped places, right? This vector, which was, further down if you rotate clockwise, it's now the first one that you reach when you rotate clockwise. Okay, you flip things around. A Jacobian determinant, if this is the relationship, the Jacobian determinant is going to give you a negative number. The magnitude of the Jacobian determinant tells you how much the measure of the area has changed. But the sign tells you that you've also flipped things. Now, we don't care if things flip here, okay? Which is why we have the absolute value. We just care about that change in the measure of the region which we are integrating over, okay? Let's look at a couple of examples where we're just applying the Jacobian determinant. Let's look at a couple of examples that we're familiar with. So let's make the change from rectangular coordinates to polar coordinates in a double integral. Okay. So I'm not going to worry about the region over which we're integrating or the function. I want to know if we make this change, to polar coordinates, what's the Jacobian determinant going to be? Now, we've already covered making the switch to polar coordinates, so we know what the Jacobian determinant should be. It should be r, right? Let's confirm that, though. So my Jacobian determinant here, I need the partial derivatives of x and y with respect to r and theta. Okay? My new variables are r and theta. So I need to be able to express x and y in terms of my new variables r and theta. Well, we remember that x is equal to r cosine theta, and y is equal to r sine theta. So now with x and y expressed in terms of my new variables r and theta, I can take the partial derivatives and plug into my Jacobian determinant. Okay, let me just put an underline there to remember that that's missing, right? We need to plug that in. That's what we're looking for. So partial derivative of x with respect to r is just cosine theta. Partial derivative of x with respect to theta would be negative r sine theta. Partial derivative of y with respect to r is going to be sine theta. And partial derivative of y with respect to theta would be r cosine theta. Okay, take the determinant, the 2 by 2 determinant, so multiply this way, that's r cosine squared. And then subtract what I get when I multiply this way, so that's going to be minus negative r sine squared theta. Of course, the double negatives become plus. I can factor out the r, leaving me with cosine squared theta plus sine squared theta. Cosine squared theta plus sine squared theta is just 1. And look at that, I do get r, which is just what I expected to get. Okay? So the math works. Let's try it one more time for a triple integral. Let's try spherical coordinates. So let's try rectangular coordinates to spherical coordinates. Okay, so again, we're not going to focus on the actual function or the actual region. I just want to, for this example, focus on that Jacobian determinant. So if we go to spherical coordinates, to our new variables, rho, theta, phi, we already know what the Jacobian determinant should be. From what we've already done, this should be rho squared sine phi. So let's double check that the Jacobian determinant actually gives us that integrating factor. Okay, so we would need the partial derivatives of x, y, and z, our old variables, with respect to the partial derivatives of our new variables, rho, theta, and phi. Okay, so partial derivative of x with respect to rho, with respect to theta, with respect to phi. The partial derivative of y with respect to rho, with respect to theta, with respect to phi, and the partial derivative of z with respect to rho, with respect to theta, and with respect to phi. Okay, so let's grab our relationships between our old variables x, y, z and our new variables rho, theta, and phi. We know, just because we've dealt with spherical coordinates before, that we want x to be rho sine phi cosine theta. Y should be rho sine phi sine theta. And z should be rho cosine phi. Okay. Our old variables are each expressed in terms of our new variables. Okay. So let's plug in the partial derivatives. Partial derivative of x with respect to rho would be sine phi cosine theta. Partial derivative of x with respect to theta would be negative rho sine phi sine theta. And finally, partial derivative of x with respect to phi would be rho cosine phi cosine theta. Okay, next column, partial derivatives with respect to y. I'll move a little bit faster here. Partial derivative of y with respect to rho is sine phi sine theta. With respect to theta is sine phi cosine theta. And with respect to phi would be, rho sine phi sine theta. And with respect to phi would be rho cosine phi sine theta. And one more, partial derivative of z with respect to rho is cosine phi. With respect to theta, there are no thetas in this expression, so it's just 0. And with respect to phi, I get negative rho sine phi. All right, let's take the 3 by 3 determinant. This is just like taking a cross product. Okay, so worry about this. Okay, I'll get this times that minus that times that. Okay, so that's rho squared sine squared phi cosine theta with a negative in front. Rho squared negative rho squared sine squared phi cosine theta minus this times this, that's just 0. Times this guy, sine phi cosine theta. Sine phi cosine theta. Okay? Next component, this guy. Cancel out the row and column with it. Okay? multiply those two, then subtract what I get when I multiply those two. So this times this, that's a positive rho squared sine squared phi sine theta. Rho squared, you know what? Let me write on the next line. I know I'm going to run out of room here. Rho squared sine squared phi sine theta minus that, which is just 0, times this, right? Because I'm expanding about that sine phi sine theta. Okay, and then my final component here, multiply these two, and then subtract what I get when I multiply those two. Okay, so negative rho squared sine phi cosine phi sine squared theta. Negative rho squared sine phi cosine phi sine squared theta minus what I get when I multiply those two, which is rho squared sine phi cosine squared theta. Rho squared sine phi cosine squared theta times, remember I expanded about cosine phi, so I need to multiply by that at the end here. Cosine phi. Okay, alternate signs, plus, minus, plus. Okay, that looks like a big mess. But there's a lot of squared sines and squared cosines, so maybe I could do something with that. All right, so let's see what I can do here. For this first line, the 0 just goes away, so I just have this times this. So I will have negative rho squared sine cubed phi cosine squared theta. Here, down here, I have rho squared sine squared phi sine theta times sine phi sine theta with a negative in front. I get negative rho squared sine cubed phi sine squared theta. And then down here, what I notice right away is that I have a sine squared and a cosine squared, and the coefficients of both, the expression in front of both is the same. So I'm going to factor out a negative rho squared sine phi cosine phi. I'm going to multiply it by the cosine phi that's over here too. I'm going to factor out a rho squared sine phi cosine phi. Multiply it by that cosine phi, so I get cosine squared phi. That'll leave me with a sine squared theta plus cosine squared theta inside the parentheses. Leaves me with those two. Okay, and of course that's just one. Beautiful. It's already helping me simplify. All right. Just a little bit more to go. I could do a similar thing here. If I factor out a negative rho squared sine cubed phi from both of these, I'll be left with a cosine squared and a sine squared. Okay, so negative rho squared sine cubed phi, left with cosine squared theta plus sine squared theta. And then I still have this minus rho squared sine phi cosine squared theta over here. Oh wait, it's cosine squared phi, isn't it? Yes. Phi. This is also just 1. And now I notice I have a rho squared sine cubed phi here, and I have a rho squared sine phi here. So I could pull out the rho squared and one of the sine of phi's, right? And also the negative in front. Let's pull all that out. Negative rho squared. I'll pull out one of the sine of phi's. I pulled out one of the 3, so that leaves me with sine squared here. I pulled out all this, so it leaves me with cosine squared here. And that's just 1. And so the Jacobian determinant is negative rho squared sine phi. That's pretty much what we were expecting, right? The only thing left to do is to remember that when we plug it in, when we plug it in, we were expecting positive rho squared sine phi, and we got negative rho squared sine phi. Remember, when we plug in, we always take the absolute value, right? So this is going to be the absolute value of our Jacobian determinant. So that'd be the absolute value of negative rho squared sine phi, which is exactly what we expect. Positive rho squared sine phi. Okay? So that gives you an idea of how to do those Jacobian determinants, and it confirms the results that we have already looked at. That when we convert to polar coordinates, we need that extra factor of r to make it work. When we convert to spherical coordinates, we need that extra factor of rho squared sine phi to make it work, to offset the changes that the transformation applies to the space. So let's take a look at a fuller example where we have to evaluate a full double integral using a change of variables. So here we're integrating this function, sine of x plus y over 2 cosine of x minus y over 2, over the triangular region with these vertices. And we're going to do it by making the change of variables u equals 1/2 x plus y, v equals 1/2 x minus y. So right off, you could see why this would be a useful change of variables. If you try to take the antiderivative of this thing with respect to x or with respect to y, we're kind of flummoxed. There's not an obvious way to do that. Maybe you could do something with trigonometric identities, but making this substitution, we can immediately see the benefits of that, because that would change the entire input of the sine function into just u, right? And the inside of the cosine function into just phi. Okay? So what do we need to do? Well, we need to find the Jacobian determinant. If we're going to make the substitution, we need to figure out that integration factor that is going to offset any changes to how we stretch out or squish the region of interest here. Okay, so let's start with that. We already have u and v expressed as in terms of variables x and y, so that's good. Okay, so let's find the Jacobian determinant of xy with respect to uv. Okay, by the way, let me show you one other way that we sometimes write this. So if we just have juv, that's also the Jacobian determinant with respect to variables uv here, just in case it comes up. It means the exact same thing. Okay, so we want the determinant of the partial derivatives, partial x partial u, partial x partial v, partial y partial u, partial y partial v. And looking at what u and v are here, let me just write them here for reference. We can pretty quickly see that the partial derivative of x with respect to u. Oh, actually, you know what? We're in the wrong order here, aren't we? We know what u is in terms of x and y. We know what v is in terms of x and y. But we want x in terms of u and v. We want y in terms of u and v. So we want to switch the orders around. We want to solve this for x. We want to solve this for v. Okay? So we could do that with a little substitution, with a little elimination here. What I'm going to do is I could add these two equations together. I get u plus v. Let's see, let me write it this way. So if I add these two equations, I get u plus v on the left-hand side, and on the right-hand side, half x plus a half x is a whole x. Half y minus half y goes away. So x is just u plus v. And if I subtract them, then I get u minus v is equal to a half x minus a half x goes away. Half y minus negative a half y becomes y. Okay? So by adding and subtracting the equations, we could solve for x, we could solve for y. We're just using the principles that we have for solving systems of equations, just solving for another variable. Okay? All right, now these are in the form we need. We need them to be x equals something in terms of u and v, y equals something in terms of u and v. That's what we have. Okay, so partial derivative of x with respect to u is going to be just 1. Partial derivative of x with respect to v is 1. Partial derivative of y with respect to u is 1. Partial derivative of y with respect to v is negative 1. Okay, and so we get negative 1 minus 1. So negative 2. Okay, that's our Jacobian determinant. We'll take the absolute value of that and multiply it into our integrand to adjust for the offset of this transformation. Okay, so if we kind of work with what we got so far, we're integrating over region R, this triangular region. Oh, and it's a double integral. We have sine of x plus y over 2, cosine of x minus y over 2, integrated with respect to x and y. We're changing this to an integral over u and v. So we get sine of x plus y over 2, that was u. Cosine of x minus y over 2, that will be cosine of v. And we're going to get the absolute value of that Jacobian determinant of negative 2 that we calculated. Okay, what we still need to find are the limits of integration. We know we're going to be over a new space in our UV space. So we need to translate R to our new space in R star. Okay, our new region in UV space. Okay, so let's illustrate that. So here's XY space. We have the triangular region with vertices 0, 0, 2, 0, 1, 1. 0, 0, 2, 0, 1, 1. That's region R. Okay? What we want to do is we want to translate that into our new space, UV space. Okay? What we want to do is we want to take each line that we have here in XY space and translate it to UV space. All right, so let's first find the equations of these lines in XY space. They're pretty easy. This bottom line, just on the x-axis, so that's just y equals 0. This line goes from 0.00 to 0.11. So we're going up 1 over 1. That's the line y equals x. Okay. And then this line here. Okay, we could see we are going right 1, down 1. So the slope is going to be negative 1. And I'm going through the point, let's say this point. That's the point 2, so x minus 2 plus 0. Okay, so the line is y equals negative x plus 2. All right, so we have our lines. What we need to do is we need to translate those lines to what they would look like in UV space. How does the transformation apply to them? So for y equals x, take the lines one at a time. Y equals x. If I look here, I notice I have x minus y, I have x plus y. So I want to translate this so using these tools here to UV space. Okay, now I could just plug this in for the x and this in for the y, okay? But I could be a little bit smarter about it if I subtract the y to the other side and then multiply by 1/2. Okay, then I get 1/2 x minus y. That's exactly what v is. Okay, so my first line here is v equals 0. That's this line here, and maybe I should color code these. This line here, when I translate it to uv space, it's v equals 0. So that'll be this line here on the u-axis. Okay, and it goes from this point to this point. Okay, so that was the point xy equals 0, 0. So let's write that down. From xy equals 0, 0 to xy equals 1, 0, right? This line here, going from 0, 0 to 1, 0. Okay, so let's translate both of these points to what they would be in UV space. So if x and y are both 0, 0, then I could see my u is 0, my v is 0. Okay, so uv also equals 0, 0. And if I plug 1, 0 in here, so if I plug in 1 for x, 0 for y, I get u equals 1/2. So uv space, the u will be 1/2. And if I plug x equals 1, y equals 0 in here for the v, I get 1 minus 0 times 1/2, so I get 1/2 again. Okay. Oh, wait a second. I've got the wrong point here. This doesn't make sense, right? Always good to be able to recognize when you have a situation. This wouldn't lie on this line. This line has to always have v equal to 0. Okay. The issue is that I picked the wrong point. I wanted this point. I picked this point. Okay. So this point should actually be 1, 1. And how is that going to change my point in UV space? So if I plug 1, 1 in, 1 plus 1 is 2, divided by 2 is 1, so the u is 1. And then 1 minus 1 is 0 times 1/2 is 0. Okay, that makes more sense. Now the v is 0 for both. They both lie on this line. Okay? So this point becomes this point in UV space. This point, the point 1, 1, becomes the point 1, 0 in UV space. And the line, y equals x, becomes the line v equals 0 in UV space. Okay? So you need to translate each edge, each curve, from one space to another. All right? Let's take a look at another one. Let's take a look at y equals 0. Okay? So for y equals 0, what's the best way to approach that? I could just plug it in here. Okay? Y equals 0, I'm just going to plug u minus v in for y. And so that means u and v are equal. Okay? So it's going to be this line here. All right? Now what I need to do is I need to find the bounds. This line will go from 0, 0 to 2, 0. So from xy equals 0, 0 to xy equals 2, 0. So again, I'm going to plug those in to figure out what my u and my v are. So 0, 0 I've already done, right? When xy is 0, 0, u and v are also 0, 0. What about 2, 0? When x and y are 2, 0, this one I will have to plug in. So let's go back to our formulas here. When x is 2 and y is 0, u is going to be 1. And when x is 2 and y is 0, v is also going to be 1. Okay, so I'm going to go from this point 0, 0 to this point here, 1, 1. Along the line v equals u. Okay? All right, and we have one more edge to look at. This edge right here, the line y equals negative x plus 2. Okay? I could, again, just plug in u plus v for x, u minus v for y. That would work. But I see that if I add x to the other side, I get x plus y equals 2. And if I multiply by 1/2, I get 1/2 x plus y equals 1. 1/2 x plus y is exactly what u is equal to. Okay, so this is just u equals 1. And it's going to go from the point. Let's go from this point here. That's the point 1, 1. From xy equals 1, 1 to xy equals 2, 0. This point right here. Okay, so I need to find those endpoints in UV space. When u and v are both 1, 1, now these points I've already done. When x and y are both 1, 1, u and v are 1, 0. And at the point where xy is 2, 0, the equivalent uv point is 1, 1. Okay? So I'm looking at this line right here. Along the line where u is constantly 1, v could be anything, and it's between these 2 points. All right? So this is my R star. That's my new space that I'm integrating over. Okay? All right. I've done most of the hard work here. Now we just have to do what we have done for several sections now. We're going to slice this region up because I'm integrating over UV space. So I need to slice up the region in UV space. Okay? Doesn't look like there's a big difference whether I slice it one direction or the other. So I'll slice it vertically, which means I'd integrate first with respect to v, right? So I've got an absolute value of -2. I'm going to just pull that 2 out front since it's a constant with respect to all the variables. Get sine u cosine v. I'm going to integrate first with respect to v. So each slice starts on the line v equals 0 and ends on this top line. And I should have labeled these when I found them. We already found them, right? V equals 0, that's that line. U equals v, or v equals u if you prefer. And u equals 1. Okay, so I'm going from v equals 0 to v equals u. And then once I integrate with respect to v, I'm going to limit myself to just the u-axis, squish it along the v direction. And u goes from 0 to 1. Okay? And that's the integral you have to perform. Much easier than the integral we started with. Okay? This one you could try it. I don't think there's any way to do that in XY space. But this one, very straightforward integral. Okay? Again, I will leave you to actually do the integration. But that would be how you do a general transformation, a change of variables over multiple integrals. Let's take a look at one more example. We're going to find the double integral over a function over region R, where R is a parallelogram enclosed by these lines. Now, this problem doesn't specifically say that we should use change variables. Let's see why that would be a good idea. If we sketch out this region, it becomes pretty clear that if we could do a change of variables to make the region a little nicer, something we would want to do. Okay? And so we have x minus y equals 0. That's y equals x. X minus y equals -3. That's the line y equals x plus 3. So same slope of 1, y-intercept of 3. Then we have 2x plus y. I can rewrite that as y equals -2x plus 2. So -2x, so down 1 over 1. Get this line right here. And finally, this one, y equals -2x plus 7. So 1, 2, 3, 4, 5, 6, 7. Down 2 over 1. So this is the region here that's enclosed by all 4 lines. That's our parallelogram. That's the region over which we integrate. Okay? And integrating over this may not be very pleasant because I'd have to break it up into multiple pieces to be able to integrate. Okay? If I slice it up in the y direction, I could slice it up to here, but after that, the curve that determines where my slice begins and ends changes. Right now, it's starting on the green line and ending on the yellow. But after this, then, oh, look at that. It starts on the blue and ends on the yellow. Different starting point, which means I'd have to use a different double integral to calculate that portion. And then eventually, not too long after that, it swaps again. Starting on the blue and ends on the purple. The ending line is different. And so I'd actually have to do 3 integrals as it currently stands. One for this region, one for this region, one for this region. I don't want to do 3 double integrals. Okay? What's more, even if I did that, it's not very clear that I'd be able to take the integral. This isn't a super nice integrand. I think it's doable, but it's not nice to work with. But what we do notice is that each one of our expressions on the left-hand side of these equations here, either x minus y or 2x plus y, that's exactly the same expressions I have in my fraction. So I could take advantage of that. Okay, so I'm going to make a change of variables. This would all be a lot simpler if u was x minus y and v was 2x plus y. Okay, then these 2 lines would be u equals 0 and u equals -3. These 2 lines would be v equals 2 and v equals 7. And my integrand here would just be u divided by v. That all sounds a lot simpler. Okay, so let's make the change of variables. So I'm going to need my Jacobian determinant. Okay, my Jacobian determinant is going to be partial of xy over partial uv. It's the determinant of all partial derivatives. So partial x, partial u, partial x, partial v, partial y, partial u, partial y partial v. Okay, now I'm not quite ready to take these partial derivatives yet because I haven't expressed x and y in terms of variables u and v. I have the opposite right now. U is expressed in terms of x and y. V is expressed in terms of x and y. I want to take this system and rearrange it so that x is by itself on one side and just u and v is on the other side. So that y is by itself on one side and so that just u and v are on the other side. Okay? So what could I do here? U equals x minus y, v equals 2x plus y. Right off, I see that I could add them together. Okay, because it would eliminate the y. I get u plus v equals 3x, which means x is 1/3 u plus v. Okay, so x is 1/3 u plus v. Now, next, I could take the same system, u equals x minus y, v equals 2x plus y, and I can multiply this first equation on both sides by -2. Okay, if I do that, I'm going to get -2u minus 2x, and then double negative plus 2y. I do that because I notice I can cancel the x's that way. Okay, 2x will cancel with -2x. And so doing that, I get v minus 2u equals, the x's cancel, and 2y plus y is 3y. So I get 1/3 v minus 2u equals y. Okay, so y is 1/3 v minus 2u. Okay, all right. We have x in terms of u and v. We have y in terms of u and v. Now I could take those partial derivatives. Partial derivative of x with respect to u is just going to be 1/3. Partial derivative of x with respect to v is also 1/3. Partial derivative of y with respect to u is going to be -2/3. And partial derivative of y with respect to v is going to be 1/3. So I do the determinant. 1/3 times 1/3 is 1/9. -2/3 times 1/3 is -2/9. And then I want to subtract that, right? So I'm going to get double negative there. I get 3/9 or 1/3. That's my factor. That's my Jacobian determinant. That's what I'm going to have to multiply by in the integral once I change the variables to adjust for the stretching and transformation that happens when I change variables. Okay? So I've got my Jacobian determinant. Let's start building my integral. So the integral I started with was x minus y over 2x plus y. Okay? So integral over r of x minus y over 2x plus y integrated over area. I'm going to change it into an integral over uv space. X minus y is u. And 2x plus y in the denominator here is v. So I get u over v, and then times the absolute value of the Jacobian determinant, which in this case is 1/3. Okay, now we still need to decide our order of integration and our limits of integration. To do that, we need to translate this region in xy space to a region in uv space. So let's just start with the lines themselves, and we'll find that that actually makes things a lot easier. Once we get the lines down, it should be straightforward. This first line here, y equals x, that was x minus y equals 0. But x minus y is u, so this is just going to be u equals 0. Okay? u equals 0, which is the v-axis. Y equals x plus 3, this line here. We start off by calling it x minus y equals negative 3. U is x minus y, so that would be u equals negative 3. That would be, extend my range here a little bit, negative 1, negative 2, negative 3. That would be this line here. Nope, wrong way. That would be v equals negative 3. Let's extend this way. Negative 1, negative 2, negative 3. There we go. Okay. And then we have y equals negative 2x plus 2, which started off as 2x plus y equals 2. 2x plus y is just v, so that would just be v equals 2. And then finally, y equals negative 2x plus 7 is the same thing as 2x plus y equals 7, which is v equals 7. So 1, 2, 3, 4, 5, 6, 7. And so this problem is a little less work than the other one because we could see the region that we're dealing with here is this one right here. Okay. And so I just need to decide which way I'm going to slice it up. Let's slice it up in the u direction first. Why not? We're over a rectangular region, so it's nice and easy. Every slice here in the u direction, holding v constant, starts at u equals negative 3 and ends at u equals 0. So integrating first with respect to u from negative 3 to 0. And now let's integrate with respect to v. So once we integrate with respect to u, it collapses that dimension. I'm left with only v. And we could see v is going to range from 2. I've kind of covered it up here. But v equals 2 to v equals 7. Okay. That is a much nicer integral to work with and over a much nicer region. As usual, I'll let you actually evaluate the integral, but that is how you set it up.